So in part A, we're told that X is the matrix 2, 0, 0, 1, negative 3, 0. And Y is the vector 2, 3, 4. And our goals are to find W star, that is the optimal amounts to take of X, the first column of X and the second column of X, in a linear combination that gets as close to Y as possible. We want to find P, which is the actual vector that results from multiplying X by W star. We want to find the error vector, which is how far Y is from P. And we need to verify that this E, error vector, satisfies the orthogonality conditions that we implied in that geometric diagram just a moment ago. OK, let's go. We know that W star is X transpose X inverse X transpose Y. And so this is kind of, it requires a bunch of calculation. And in another video, we're going to show you how to use NumPy quickly to do calculations like this. But for now, let's see if we can do this quickly. Remember, X transpose X, whenever you see this, you should think what I'm producing is the dot products of all columns of X. OK? How many columns does X have? 2. So X transpose X is going to be a 2 by 2 matrix. What is the first column dot product itself? That looks like just 4 because I have zeros here. What is the first column dot the second column? That's just 2. So a 2 is going to appear in both of these positions. And what is the second column dot itself? That's going to be 1 plus 9, which is 10. Now I have to invert X transpose X. We know this is going to be 1 over its determinant. What is its determinant? 4 times 10, which is 40, minus 4. So I'm going to have 36, times what I get when I swap the 10 and 4 and negate the 2's. So this is X transpose X inverse. Now all I need to do is multiply this by X transpose and then multiply it by Y. So we can do that. Let's rewrite this a little higher. 10, negative 2, negative 2 and 4. And then up here, I'm going to have a 1 over 36. No need to distribute just yet. Maybe having the 1 over 36 up front will keep the calculation simple. Now I got to multiply this thing by X transpose. So that's going to be 2, 0, 0, because the first column turned into the first row, and 1, negative 3, 0. And then multiply this by Y. OK, let's do this. Notice I'm going to save the multiplying in Y step till the very end, because you'll see that'll allow us to make our work a little simpler when we get to part B, because there, essentially, it's the same question, just with a different Y. So let's do some of this multiplication. I have 1 over 36. Dot product of 10 and negative 2 with 2, 1 looks like 20 minus 2, so I'm going to have an 18. Dot product of negative 2, 4 with 2, 1 is negative 4 plus 4. That's going to be a 0. By the way, we should verify what the shape of this thing is going to be. This is 2 by 2. This is 2 by 3, so I'm looking for 2 by 3. Good, that's the first column. The next column is going to come from multiplying this in. That product is 0 plus 6, which is 6. The next one is negative 12. And the last one, fortunately, they saved us and gave us zeros. Good. And now you can see some of the numbers simplify in nicely, so I might just do that. 1/2, 1/6, 0, and 0, negative 1/3, 0. Keep this matrix in mind. This is X transpose X inverse X transpose. Now I have my 2, 3, 4 down here. And when I multiply this in, I get, let's see, in the first row, I get 1 plus 3 over 6. And in the second row, I get negative 1. That's 3 over 2 and negative 1. Good. And this matrix, again, for reasons you're going to see in just a moment, X transpose X inverse X transpose, I'm going to write over here. I'll write it small, but we'll write it up bigger later on for reasons we'll see. OK, so this is our W star, 3 over 2 and negative 1. That's telling us if what we want to do is make a linear combination of X's columns that's as close to Y as possible. The way you do that is by taking 3/2 of the first column and negative 1 of the second column. So what is that actual projection? 3/2 and negative 1. That's not the projection. The projection is x times that, right? So P is xw star, which is x times 3/2 and -1, okay? Which is going to be 3/2 of the first column, so 3/2 of 2, 0, 0, plus -1 of the second column, 1, -3, 0. That looks to me like 3, 0, 0, plus -1, 3, 0, which looks like 2, 3, 0. Okay? So this is the best vector that can be made as a linear combination of x's columns. And it's the best because among all linear combinations of x's columns, it is the one that is closest to y. Now, let's verify that this actually makes sense. Let's look at y itself. It has the components 2, 3, and 4, and this p has 2, 3, and 0. Okay? How do I know this is the best possible linear combination of x's columns? Well, if I look at x's columns, both of them have zeros at the bottom, which means any linear combination of them is also going to have a 0 at the bottom. What that means is there's no way of matching the 4 down here. I'm going to have to end up with a 0 there, right? Because any linear combination of these is also going to have a 0 there. So the best I could do is just match the 2 and 3 in the first two components, which means there's no other linear combination of x's columns that could be any better than 2, 3, 0. Okay, what is the error vector? Well, it's y, which is 2, 3, 4, minus our approximation of y, which is 2, 3, 0, which looks like 0, 0, 4. And finally, I think we were asked to verify that this error vector is orthogonal to both columns of x, and indeed it is. If you take 2, 0, 0 and dot it with 0, 0, 4, well, their zeros are in different positions, or their non-zero values are in different positions, so their dot product, that dot dot is 0, and similarly, this dot dot is also 0. Okay, so we've satisfied all of the requirements of part A. Now in part B, we're asked a question that on the surface may sound different, but is really the same question, just with slightly different numbers. Okay? There we're told, find scalars a and b such that a times 2, 0, 0 plus b times 1, -3, 0 is as close as possible to the vector 2, 3, 4. Oh, sorry, not 2, 3, 4. That was what we used in the last one, 1, 9, 2. Okay? This is really just the same question as the last one, just with a different y vector. Okay? Why is that? Well, it's these two vectors were just the columns of the x that we were just working with, 2, 0, 0 and 1, -3, 0. And as we saw when we found w star in part A, all we were doing was finding what scalars to multiply the two columns of x by to make that optimal linear combination. So this is really just the same question, just with a different y. Which means the w star here will be x transpose x inverse x transpose, just our new y. Why don't I call this y new for now? Okay. But this x is the same as before. So now you can see why I saved x transpose x inverse x transpose up here, because I can just be a little lazy and copy paste that down here. Okay. What does this end up giving me? On the top, I get 1/2 plus 9/6. And on the bottom, I get -3. What is this simplified to? 1/2 plus, what is this? 3/2, 2, -3. Let's just verify that we did this correctly. If you plug in 2 for A and -3 for B, in the first component, you get 4 minus 3, which is 1. Second component, you get 0 plus -3 times -3, which is 9. And in the last component, you're going to get 0. So using the same principle from before, we were able to exactly make the components 1 and 9 up top. But that last component we couldn't reach because the two building blocks we're working with have zeros in the third component. OK, so it seems like we did this correctly.